Hello guys, welcome back to class. In this session, we'll continue the distributed systems. So in the previous session, we have seen communication with, the last topic is communication in distributed systems. Now let's start with types of failures in the distributed system. So distributed system is, you can assume definitely there are failures. Some common failures, most common failures. You can also call it as a failure models or types of failures. Fail stop failure, crash failure, omission failure, and Byzantine failure. So 4 categories most commonly we refer. So first one, fail stop failure. Node halts completely or permanently. Means the node is completely not working. We can call that as fail stop failure. So completely not working or completely permanently not working. You can call it as fail stop failure. So we can detect this failure via heartbeat checks or message responses not coming from that. So we can understand this is completely failed. Example, server crashes and health checker receives no pings. So completely server is crashed and health checker is not receiving any pings. Means it is not responding for any heartbeat messages. So we can mark it as failed. Is it detectable? Yes. It is easy to detect and handle it. So in a pool of servers, if any particular server is not responding through heartbeat messages, we can identify this is not running and we can mark it as this is failed. And alternatively, we can start some other server. We can initiate another server to handle the requests. So detectable and easy to manage, detectable and can be handled. You see, this is easiest type to detect and to handle. How you handle it? So system is fully not responding. We can't go and repair all that again, bring it back. So leave that, mark it as from your cluster. You can take it out and start another new machine. There's a one failure. And second is crash failure. And terminology, don't confuse. Here, the fail stop failure is a kind of crash only. But crash failure, node halts, but it does not notify others. It is not going to notify anyone. Means other nodes may not know whether it is crashed or just slow. We don't know that whether the server is crashed or slow response. Means if you send a heartbeat message, server is not responding for a specified period of time. So what to understand? Whether it is really not working, crashed, gone, or it is responding slowly. Right? So it means node becomes unresponsive. So we are unsure about whether it is dead or just lagging. Is it detectable? Yes, but directly we can't do, only suspected via timeouts and retries. So in one ping, we can't decide that. So multiple times you retry, again you send a message, no reply, no reply, no reply. Yes. It is also easy to handle only, detectable, not directly, not immediately, but it takes little bit tries to identify whether it is responding or not. And this also can be handled, no problem. Handling is okay. But because we can't decide immediately, like the previous fail stop failure, here it is not responding, we are saying that yes, the server is gone. But immediately we can't decide it. We have to do multiple tries. And third one is omission failure. node fails to respond to one or more incoming requests. Suppose you are sending some request to the node server, it is not responding. Can we decide server is failed, server is crashed, server is not working? We can't do that. In the previous session, we discussed sometimes when a server is busy with a heavy processing, it can omit some of the requests. It can omit some of the requests, right? Drop the requests. We use the term drop the request. It can drop some of the it can drop some of the request. So it is not responding for your requests. It doesn't mean that server is not working, a server is crashed. Maybe server is running, currently it has a lot of load. Because of heavy load, it is dropping other incoming requests. So in that case, immediately we can't say that, no, immediately we can't say that it is failed. So this could be due to the network issue, it is not responding, or overloaded burden, or a partial failure. There may be any reason. So it is a omission failure. And node receives a request, but it drops it silently due to heavy CPU work or some other reasons. What's the behavior here? It may respond to some request, may ignore some other request. Why it is responding to some and ignoring some? It is ignoring some requests because of heavy load or any system partial failure happened. So it is unable to process so much. That means system is running, but it is unable to handle heavy load. So it may ignore some of the requests. In that case, system is not responding to some of the requests. That kind of failure we call as omission failure. This is also easy to fix, right? On the next one, Byzantine failure. So this is a different case. Tough to identify, but yes, node behaves abnormally, arbitrarily, or maliciously. Means it sends, maybe it is working, system is running, maybe it is sending a false data or inconsistent data, or it is doing the wrong steps, is not doing as intended. Why? That may be due to some bug, or maybe hacker attack. Due to some bug or due to some hacker attack, system is responding, but responding abnormally. Maybe sending a wrong data to you or doing unintended actions. Maybe the reason is some bug is there, because of that it is behaving differently, or maybe some hacker attack. So node sends corrupted data or misleading messages. In that case, we can say the failure as Byzantine failure. So is it more complex to handle? Yes. Immediately we can't say that. So you have to identify, you have to, if it is a attack, if it is a hacker attack, then it takes time to rectify this. They're the common failures you can see in a distributed systems, right? And just do all comparison at one place. Node behavior, it is a fail stop, halts permanently, gone. Crash failure, halts silently. Omission failure, skips requests or drops messages. It is running, but it is just skipping. Byzantine failure, arbitrary behavior. Detectable, yes. Crash failure, no. Means not immediately, additional things. Omission failure, yeah, partially you can detect. Byzantine failure, no. Means immediately we can't do that. Server example scenarios, fail stop means server down and marked as unhealthy. Whenever server down, if you have health checkup, then whenever server is not responding or down, immediately we can mark it as unhealthy, so that your load balancer will stop sending the request to that. So easy. And crash failure means node freezes, but does not alert anybody. That And omission failure, overload service, so not responding. Byzantine means compromised node, sends the bad data. This is the hardest to handle. Fail stop is easy to handle because if health check mechanism is there, it will easily handle it. Crash and omission are bit moderate to handle these problems. Okay, these four are the kinds of problems you can see in a distributed systems. Next, very important. Try to understand carefully. Any questions you have on the way, you ask, clarify this. Most important concept in the distributed system. So anybody who is trying to design the distributed system, first they must understand CAP theorem thoroughly. So CAP theorem is one of the most foundational principles in a distributed system design. It highlights the fundamental trade-off between three guarantees. Consistency, availability, and partition tolerance. C is the consistency, A is the availability, and P is the partition tolerance. You can also call it as partition tolerance, network partitioning also. Three things: consistency, availability, and partition tolerance. So what the CAP theorem tells, by seeing the screen, what do you understand? Why CAP theorem? Why CAP theorem, guys? CAP theorem is to trade off between three guarantees. To trade off between three guarantees. Trade off between three guarantees called CAP. So I hope you already understand the consistency in the previous sessions. We have seen about consistency discussed already, but we will discuss again. You have an idea about what is consistency. You have an idea about what is availability and partition tolerance or network partition. Definitely, distributed systems will have network issues. We have to assume that your distributed system always will have the networking partition. Partitions are there, means you have networking issues always. So when you design, no, Swati, that is not about SQL or no SQL. This is not specific to any database. It can be any distributed system. For example, if you take, so all of you know about DynamoDB, right? DynamoDB, for example. What is DynamoDB? Is a database. It's a NoSQL database. DynamoDB is a distributed system. Is a distributed application. DynamoDB is a database, means it is an application written, right? It's an application written. It is a distributed application. You take the Netflix, a distributed application. YouTube, distributed application. Facebook, a distributed application. Instagram, a distributed application. So you can develop banking systems nowadays. All banking applications, distributed applications. You have e-commerce applications are distributed applications, right? So when you design any distributed application, these three guarantees you have to choose what is required and what is not required. Okay. Generally, consistency required for a data applications or not. You are developing some application, guys. It may be anything, banking, or I'm not telling in a specific domain. Generally, you are developing a distributed application. For a distributed application, consistency required or not required? Consistency required or not required? Very good. Depending on the case. But generally consistency means correctness, right? Consistency means correctness, correct data. Generally, do you want to maintain a correct data or not? Consistency means correctness, correct data. So generally, any application you develop, you need to maintain a correctness of a data always. So consider yes. Then availability, definitely availability also required. Applications should run up and run always whenever it is required. And partition tolerance, yes, networking related will have issues. So starts with CAP theorem provides trade-offs between three important guarantees called consistency, availability, and partition tolerance. Okay. So this CAP theorem introduced by Eric Brewer, you can also call it as a Brewer theorem. People are calling as Brewer theorem or CAP theorem. What it tells, this I am taking as initial statement of CAP theorem. So we'll take a initial definition first, understand, then we'll conclude something as a final statement of CAP theorem. Two ways I defined it: initial statement of CAP theorem and final statement of CAP theorem. So let's start with initial statement of CAP theorem. So what this Eric Brewer defined is, it is impossible for a distributed data store to simultaneously provide more than 2 out of the following 3 guarantees. So what it is telling? More than 2 out of 3 guarantees. More than 2 out of 3 guarantees. It is impossible to provide more than 2 guarantees from these 3. It means from CAP 2 guarantees only. If you develop a distributed application, distributed system you are developing, for a distributed system, in reality you can guarantee only 2. More than 2 impossible, means 3 guarantees. If you say I am developing a distributed application, and for me I need a consistency, I need availability, I need fault tolerance, that is a partition tolerance. If you say I want all 3 guarantees, impossible. You can get only 2. What 2 can be? Maybe you can get CA, consistency, availability. Yeah, I'm writing all the possibilities first. CP or maybe AP. So your distributed system may get AP, availability or partition tolerance, or distributed system may get consistency or partition tolerance, and maybe consistency and availability. Possibilities are 3. Any 2 you can get, means only this you can get these 3 possibilities. But in reality, it is not possible for a distributed systems. You may have this or this. The distributed systems you are going to design, develop, or maybe CP systems or AP systems. It means the systems provide partition tolerance and consistency, or partition tolerance and availability. So whatever distributed system you are developing, partition tolerance is must. It means if you have a distributed system, there are 3 computers connected through a network. Network failures will be there or not? Network failures will be there or not? Any chance to avoid network failures? Can you say that we won't find network failures? Network failures always will be there. You can say network failures are must. So always you have to pick P. So already you selected a P, because partitions network failure means systems are separated. Suppose these 2 are not working, guys. This network failure, these 2 are isolated, right? These 2 are isolated. There's no communication between these 2. It means because of network failure, this node A and B are disconnected. If node A and B are disconnected, you call it as partition is there. Partitioned, these are partitioned, separated, divided, isolated. Now, so any system, you have to consider P always. Now you decide you want either consistency or availability. You will get any one from consistency or availability, either C or A. P is a must. So you will get only two guarantees. More than two means total three only, three impossible, right? Okay. So let's understand what is consistency. Already we have seen previously, but in the context, I have written just few points. So every read receives the most recent write. Every read receives most recent write. If that is the case, you can call it as system is consistent. System is consistent. That is, if user writes a value to system, any subsequent read must return that updated value or recent value. It should not give a stale data, right? It should not give a old data or a stale data. If system is providing most updated data always, then it is called as consistent system. Remember, the consistency we are talking here in the CAP theorem C, and the C in the acid properties. Acid properties C also consistency one. That is related to specific to relation database only. The acid transactions, acid guarantees specific to relational databases only. That C is different. This CAP's consistency is about distributed agreement on the data state, whereas acids C is about constraint enforcement. In acid, constraints state should be consistent by enforcing the rules, right? Acid C, you just revise again it, but currently remember it. C in the CAP and C in the acid are not same. These two consistencies are not same. Okay. Now back to the C in the CAP. C in the CAP tells about consistency is about a distributed agreement on the data state. When you try to read, you are getting the latest updated or stale data. Simple. If you are getting a latest data, then it is consistent state, consistent system. If you are getting stale data, then it is inconsistent. It is not a consistent system. So consistency is clear in the CAP theorem. CAPS C, then availability. Availability. Each read, maybe each request with the read or write receives non-error response. System is available. System is available. High availability or availability means system is up and running. Whenever you send a request, you will get a response. Whenever you send a request, you will get a response. You will get a response. No non-error response means it won't say that server crashed or some network problem or something. It won't say anything like that. It will give you, but it may give latest data or it may give stale data. So even if the system cannot guarantee that it is latest data, system may not guarantee that it is latest data or it is old data. It will give you the data always. That's what we are calling it as available. System is available means it is always up and running. For every request, you will get a response. What is availability, guys? Whenever user is sending a request, there should be a system to respond immediately. Yes, system is available to respond. If you ask the price of mobile phone, it will give you the price. This is the old price or the latest updated price, no guarantee. But system is available. It will respond to you always. That's what availability concept. Clear? Availability also clear? Consistency, availability. Next, about partition tolerance. Partition tolerance, what is this? System continues to operate even when nodes cannot communicate with each other. System continue to operate. Systems continue to operate even when there is network failure. For example, you have node A, node B. I have a two node cluster. Simply consider as two node cluster. Two nodes are in the network through this. Now, if two systems are there, two servers are there, two nodes are there, I can send request to any node. Am I right? I can send a request to this. It will provide a response to me. Other user can send request to this. It will provide. That's what distributed, right? Distributed means you send, there are multiple people to answer your queries. There is a person A and B, node A and B. You send a request to A or you send a request to B. In any case, you will get a response. Suppose if the network is crashed, network problem between these two nodes. Now, system will continue. When you send a request, B is unable to talk to A. A is unable to talk to B. Now, when you send a request to B, whether B will respond to your request or not. Whether B will respond to your request or not. A is unable to talk to B. Now, when a user 1 is sending a request to A will respond or not? A will respond to user 1. A will respond to user 1 even if it is unable to talk to. So, there is a partition between A and B. There is a failure, network failure. So, partitioned. These are partition separated. Even though system continues to operate and provides the responses to the users, even the different nodes are unable to communicate because of some problem. This is what is known as partition tolerance. It does not mean no failure. System, I am telling system continues to operate. It doesn't mean failure is not there. There may be a failure. It means system knows how to deal with the failure. System knows how to deal with the failure. A and B are disconnected because of some network issue, guys. Because this is a distributed system, you always assume there is a problem in the distributed systems, especially in the networks. There will be a problem. Okay, so there may be some problem, but system knows how to handle this problem. Your distributed system should know how to handle this. You should not expose this problem to customer. When a user 2 is asking B, B should not say, no, I have to get a data from A, but A is not responding now. Sorry, boss, I can't respond. It can't say that. B should rectify it later. Later, it has to rectify and it has to up and run always. So, many reasons. It can handle, maybe it can handle the failures in different ways. Maybe provide the fallbacks or conflict resolution or eventual consistency. These are different terms we'll study later. Partition tolerance is clear. Even there is a failure and nodes are unable to communicate, they should still continue to operate. Means I am considering there is a failure between the nodes even though my system is continue to operate. If problems exist, then we can say partition tolerance, yes, available. Partition nodes are partition. Again about partition tolerance. So same point I am repeating. System continues to function or operate despite message loss or network partitions between the nodes. System continues to operate despite message loss. some message dropped, data packets dropped, or network partition happened, something, any reason, system has to continue. There's a partition tolerance. Now, partition tolerance is non-negotiable in the distributed system. Partition tolerance is non-negotiable. It means you always consider partition tolerance in the distributed systems. What is the meaning of that? Networks are inherently unreliable. So nodes can get a partition anytime. Nodes can get partitioned anytime. Nodes can be separated anytime, isolated anytime. Problem can come anytime. So the distributed systems you design must tolerate partitions. Systems must tolerate partitions by design. Means the design of your distributed system must handle partitions. Must handle partitions means must handle network failures, partitions between the nodes. That is, partition tolerance is not optional in the distributed systems. All distributed systems must plan for this. All distributed systems must plan for this. All distributed systems must plan for this. So now if you go back to the previous slides, here, not this. So I told here that there are 3 guarantees. According to the CAP theorem, you will get only 2 guarantees. You will get only 2 guarantees. Now, by understanding partition tolerance, can I say that your distributed system must have the P? Distributed system must have the P. P should be there. Every distributed system must have the P. You consider P. Partitions may occur between the nodes. Then we can't get more than 2. You can get 2 only. So P already you are considering. Then you have to choose either C or A. So either you will get CP or AP. Right? Little confused, no worries. Still, I have written more points on this. This is very important. The next, okay, go to the next one now. Partition tolerance is clear, right? So, in a CAP, you understand what is consistency, what is availability, what is partition tolerance. These 3 are clear, right? First, these 3 are clear. Okay. Now, one more point is partition tolerance cannot be ignored. It is not an optional one in the distributed systems. Partition tolerant must be planned for every distributed system. Okay. Must be planned for. Assume that there is a problem. Assume that there is a problem. It means you are planning for a problem. You are considering problem is there, not as a problem may come. Assume there is a network problem. Then how to handle a distributed system. So we are considering partition tolerance. We are considering failures, network failures. So P we are always considering in the CAP theorem. Remaining 2 are there. You can't get a more than 2. In that P always I am taking. I want P because problems are there. Then I can select either C or A. How it is, we'll see that. So we'll take a scenario to prove that how it works. Okay, go next. Partition tolerance means, yes, see this point. Partition tolerance means nodes are partitioned due to any problem, not only network failure, any problem. Nodes are separated, nodes are partitioned, no communication between the nodes. That is a partition tolerance. Whether your system tolerate the node partitions or not. Whether your system tolerate the partitioned nodes or not. System tolerate the partitioned nodes or not. Point is clear? Abhishek? Okay. Anyway, we have another scenario. There you will get clarity. So from the CAP theorem, final statement we are reading now. Final statement of CAP theorem is, I am considering the network partition. That is the partition tolerance. So I am assuming there is a network issue. In the presence of network partition or in the presence of some partition, distributed system choose either consistency or availability. In the presence of network partition means I am considering, boss, there is a network problem between the two nodes. The two nodes are separated, disconnected, not talking each other. That is P selected. So in the presence of P, you have two options. Either you choose consistency or availability. Either you choose consistency or availability. So any issue, voice issue for all of the guys or specific to H1 local? Are you getting all the guys' voice clearly? Fine. Okay. For you H1, I think you check it locally. So in the presence of partitioning, network partitioning, partition nodes, distributed system can choose either consistency or availability. It means the distributed systems which you are developing, the distributed systems which you are designing, either CP or AP. So if you are new to distributed system design, you should not think that in my distributed system network problems may come. Okay, I want consistency, I want availability. I want consistency, I want availability. Impossible. You cannot get both consistency or availability. You can get either CP or AP. Consistency, partition tolerance common, either consistency or available. So there is no such things like CA systems. You can't find CA systems, means consistency and available. CA systems are available. We can't say no systems, but I am telling this is the story of distributed systems. In the world of distributed systems, you don't have a CA systems. If you take a single node machines, like you take your Oracle database, guys, Oracle non-distributed Oracle database, if you take that is CA system only. Non-distributed Oracle database is CA system only. Non-distributed MySQL database CA system only. Or you developed a monolithic application for your enterprise, that is a CA system only. We are especially talking about distributed systems. Distributed systems means there is a chance for a partition between the nodes. Any problem, for easy understanding, I am taking network partition, means network problem between the two nodes, so disconnected. So I am considering P always. In the presence of P, distributed system can select either C or A. So you have only consistent plus partition tolerance systems or availability partition tolerance systems. So either your system may be consistent or available. Both not possible. Both not possible. Okay. Next. So to make the final statement of CAP theorem more clearly, I'm just taking one scenario. So imagine that there is a distributed system between two nodes. I just considered two nodes. This is node A and this is node, or I'll write in a different way. This is my node A. This is my node B. This is a distributed system, means the two nodes are connected or not. These two nodes are connected. They will talk each other. They will talk each other, right? Yes. There's a distributed system. Two or more systems connected via the network is called as a distributed system. Okay. Now, network partition occurs. Network partition occurs means there is some network issue here. Okay. It means these nodes are partitioned. These are partitioned nodes, separated nodes. A and B has a networking problem, so they cannot talk each other. Clear this point? Two nodes, but network issue. Now, user one is sending a write operation. Sending a write operation. What they are writing? X equals to 5. There may be some X value here. There may be, previously you consider, there is X value here also. 10 is there. There is X value here also. 10 is there. Previous value is there in both the systems, right? Now, what happened? So, X write operation. This X is changed to 5. Now, second user, another user is trying to read operation, trying to read X from B, node B. So, what X value will be returned? Are you getting the latest value of X? You will get the 10. Is it the latest value? So, this is the old value, which is incorrect value, called as stale data. Now, tell me whether this distributed system is consistent. Is it a consistent system? No. This is not consistent. But it is still responding or not? It is still responding to the user or not? The system is operating continuously, responding to the user requests, even though there is a network partition, but serving the stale data. So, this is not a consistent system. In this case, we have P is there because problem is partition is there, right? And it is not a consistent, but it is available. Is it AP system? Can I call it as this is AP system? Is this AP system, guys? System is available. When user 2 is asking, give me the X value, it is responding X value, it is giving some X value. It is not saying, no, I did not get the updated data of X because I'm not talking to B. I can't talk to A, problem is there, so I didn't get updated data, so I can't give you that. It is not saying like that. It is saying, okay, you are asking X value, provide X value 10. Is it old or new? We don't know that. No guarantee of this data, whether it is stale data or latest updated data. But it is responding. My system is available, B is available, A is available. So available. And there is a network partition AP, but this is not a consistent system. This is not a consistent. This diagram I'll draw here in the space only. I'll draw and give it to you. Is this clear, guys? Oh, I removed the diagram. Fine. Okay. So to ensure consistency, the system should be consistent. What it means? Node B must not return a stale data. If you want to say this current distributed system is, I'll draw it again. Node A and node B. There is a network partition in this. Network partition is there. We are always considering that. User 1 is doing a write operation with x equals to 5. User 2 is doing a read of x. So already x equals to 10 is there, x equals to 10 is there. This is updated with x. So this is getting a 10. This is the diagram, what do you understand? Okay. Now read this. If you want the system to be consistent, what is required? We understand that in this particular case, this is not a consistent system, but what has to be guaranteed when you want to make this distributed system as consistent system? To ensure consistency, node B must not return a stale data. Clear? Node B must not return a stale data. Then we can say, then if node B must not return a stale data, node B must return recent updated data, that is x equals to 5 in our context. If node B is returning the latest value of x, which is 5, then you can say it is consistent system. But node B has not received the new write because of partition. Partition means separation, disconnection. So to stay consistent, remember this carefully, listen this carefully. If you want to make this system to be consistent, then node B must reject the read request. If node B rejects the request, if user 2 is asking, I want X value, node B is, user 2 is asking, I want X value, user 2 is asking, I want X value. Two cases, give the whatever available X, or you tell boss, I don't have updated value, please. Don't go to the next level, Anik. First, let me to complete, then you ask the questions. Listen this. See, if node B rejecting the request, node B is rejecting the request, not taking the request, in that case, can I say availability is gone? Availability broken. If you want consistent only, if you want the system to be consistent, then node B has to return the latest value. If node B don't have a latest value, the node B has to drop the request, reject the request, drop the request. Then you can say that system is not available. Availability is broken. Okay. Then go to the next. If you want to make the system as available, to ensure availability, what is required, guys? Node B must respond to the read. When user 2 is asking, I want X value, node B has to respond immediately and provide the X value. If node B is responding immediately and providing X value, then only you can say that the system is high available. Am I right? If node B is providing a value, but this is a old value as of our knowledge. It is a old value means system is responding with the stale data. Responding stale data means consistency is broken. Do you understand, guys? If you want a consistency, you are losing availability. If you want availability, you are losing consistency. I think this is a more clear example of any distributed system. You will get either C or A. Do you accept this? Is this clear? Any distributed system, either C or A. Consistency is there, availability not possible. If system is available, consistency not possible. Is this clear? There's a final statement of CAP theorem. We always considered partition tolerance. There is a partition in the network, in the distributed system nodes. There is a partition. So we get either availability or consistency. Up to this clear or any queries? Now ask you queries. Or Anek asked one question, how node B knows that it should reject? That's how you have to understand now. See, now replication is not happened. Until the replication is not happened, you can, we have a replication mechanism, techniques, we can stop, we can drop the requests until the data is not replicated. The Kishore asking that, how does node B knows there is a new write? That is the replication technique already we discussed, right? We discussed all the replication mechanism. When a node A is updated, it has to be replicated to all other nodes, either synchronously or asynchronously. Replication technique we discussed. So replication should happen, but replication not happening. Maybe replication is delayed or the replication is failed because there is no network communication here. Kishore, is that clear? Node B will not come to know. Node B will not come to know. Node B will not come to know whether it is any writes happen there in other nodes or not. Node A responsibility to update to B. Similarly, write can also happen in the B also. I just considered a one scenario. Maybe a write can happen in the B also. This B write, the data updated in the B should go to A. That's what. And actually, if you revise the replication technique, replication topic whole we studied, generally we will have most of the distributed systems will have one primary, right? One master will have the write operations. Read replicas will be the multiple. Have you remembered the types of replicas we discussed? You got my point, guys? You may take a master slave replica. That is a primary slave, right? Primary replica or primary multi-master. This is a master slave, multi-master. So generally you'll have a single master most of the cases, but still we can't rule out multi-master also. There may be a chance A is taking the right operation, B is taking the right operation. Then both are acting as a master. So that replication mechanism will handle the write happening here. Automatically it has to go to all the read replicas, right? So that will be the so okay, now still I think you are standing in the same question, how to reject. How to reject, currently don't think, still we have a big story behind the CAP theorem. Let's, that you are going for a high level, like how to reject directly. This is only the very high level theory. In implementation part, we have so many things, but still we have many things. Okay. So clear? To ensure a consistency, it should not return the stale data. In that case, it should not return the stale data. In that case, it has to reject the request. Reject means don't sit down, directly reject. It should not, some mechanism it has to do, it should not return the value. Okay, that will come back. That point, okay, you hold it. In that case, system is not available. We can say availability is broken. If you want availability, then it has to respond immediately. But respond means it is responding a stale data. It means consistency gone. So either consistency or available, anyone will get it. Let's see this now. So hence, final statement of CAP theorem. Hence, you cannot have both in the partition scenario. You cannot have both. Both means you cannot have both means C and A. Both not possible. You cannot have both. So suppose here, see again, your choice now. This is how we made a trade-off. You choose. You have an options. What do you want? You choose. So allow both the halves to respond. Both halves respond means allow both A and B to respond quickly. When you want to allow respond quickly, I want availability. My priority is availability. My priority is availability means allow both to respond. Okay. In that case, you are sacrificing the consistency. You are sacrificing consistency. Your priority is availability. You sacrifice the consistency. What is the outcome? You may get a stale data, but your system is fully online. System is fully online, fully available, high available, but you will get a stale data. Stop one half from the responding. So one half means in our example, B is not responding because B is not responding. Because why B is not responding? B has a stale data. It can't give stale data for maintaining consistency. It means I want a consistency. So one half of the system is not responding because now in this particular case, I've taken A, B only. You have a B, C, D, 4 networks. Suppose update happened, write happened on the A, it has to give that A updation, it has to replicate A data, X value 5 to B, C, D, it has to replicate all of the nodes. It has to replicate all of the nodes, right? So, I want a consistency. Then don't tell others to respond for this read operation. In that, because I want a consistency, then you have to sacrifice availability. What happens? Outcome, system remains correct. System remains correct means consistent. Data is always you're giving right data, no stale data, no old data, no wrong data. But partially offline means it is not fully available. CAP theorem theory is clear, guys? Okay. So there are many real world systems. I think you have seen many of this, right? You see, there are the CP systems. So if I ask you, do you know any of the real world distributed systems which are CP? HBase. HBase is a CP. Means full consistent, sacrificing the availability. MongoDB. MongoDB in a multiple modes actually. In strict mode means it will take a MongoDB in a strict mode means it will take the consistency. Strict or write mode. Zookeeper, consistent. Redis, one flavor of Redis. Chubby from Google, Spanner from Google. These systems are the distributed systems. HBase, MongoDB, Redis, these are all distributed applications, guys. Looks databases only, but distributed systems. These distributed systems are built with CP model, consistent, partition tolerant, and availability sacrificed. Okay, but there are other machines with AP. High available, partition tolerant. Any problem comes, no issue. Partition tolerant. Suppose MongoDB, any problem comes in MongoDB nodes, will it stop serving? No, because it is a partition tolerant. And any problem in DynamoDB, will it stop? DynamoDB is a distributed database, and any node problems, it won't stop serving, right? But DynamoDB is high available because they compromised the consistency. And there are, I told you, there are CA systems. But these are traditional RDBMS systems like your MySQL, single node MySQL, Postgres single node, or Oracle non-distributed mode, or SQLite. SQLite is a database running on the Android device, SQLite, Android devices. These are the non-distributed systems, single node systems. Single node systems definitely can be in single node systems, any networking issues will come. No, partition tolerance is between the nodes. When it is a distributed system, your software, your application is running in a multiple nodes and connected with the network. There is a problem for these nodes to communicate. That is a partition tolerance exists. But a single node machines, no P at all. When no P, then always you get C and E. But in the real world distributed systems, you will not find CA systems. Partition tolerance is sacrificed in this case, but this works only in the non-distributed mode. Remember this. Distributed, either CP systems or AP systems. Cassandra, Amazon S3 buckets, SimpleDB. These are all Cassandra, DynamoDB, Couchbase, React, S3. These are all AP systems. No consistency in this. Okay. CP systems are HBase, MongoDB, Redis, Spanner, Zookeeper, etc. So these systems are designed based on this CAP theorem. Means as a design, when you design a distributed system, when you design a distributed system, first you start with distributed system. So definitely partition tolerance presence is there. Then you choose, you want either C, consistency you want for your distributed system, or availability you want. You start designing your system by choosing CRE. Right? Okay, next. When should you choose AP? That is availability partition system. Summary of, we're coming to the end of this. So choose AP systems when availability is critical for me. Availability is critical for me. I can tolerate the data inconsistency. Okay, if data inconsistent means it is a permanent inconsistent, temporary, guys. Inconsistent means permanent or temporary. Inconsistency is a permanent or temporary. This point I missed it to ask. Very good. This is temporary inconsistent. Temporary inconsistent. Eventual. Yeah, that is the term I am not using to avoid a confusion, Anik. Finally, it will lead to that all eventual consistency only. Yes. So I can bear the temporary inconsistency, no problem. I can tolerate the temporary inconsistency of the data, no problem. But high availability is a critical for my applications. Then in that case, you choose availability partition tolerance systems. You compromise on the consistency temporarily. And you may have a reconciliation strategies post partition. Reconciliation strategies post partition means what is the meaning of this? Reconciliation strategies post partition means suppose the two A and B in our sample use case, A and B network problem is rectified, guys. When rectified, are you going to reconcile the data? Reconcile means again you start replicating the A X value to B. Reconciliation done. So whatever missings happened, correct the data. Yes, correct the data. That reconciliation techniques are there. So currently, if I am providing inconsistent data to user, also no problem. Later, I'll rectify it. If you are okay with that, availability is a critical, go for AP systems. Then when to choose CP? For me, data correctness is a critical. For me, data correctness is a critical. I want accurate data. And I can afford, exactly, so banking systems are always the CP systems. I can afford pass writes rather than risking the inconsistency. I don't want to risk the consistency here. I don't want risk. I don't want inconsistent data, guys. If required, I will pause the operations for some time. Means I may make it unavailable, no problem. But correctness I want is a critical. That case you choose a C. So you understand this story also. Now, when you are designing any application, suppose you are working in a company as maybe an architect, so you are design application. Which application? Your application can be a social media application, it can be a video streaming platform, it can be a banking application, it can be a inventory application like what Abhishek is telling, inventory management system, or maybe an e-commerce application, or it is a product search engine, or it can be a ticket booking application, right? You may design any of these. Now, for these variety of domains, how you choose, you want AP or CP. Now, are you in a position to select the required model for your distributed system? If I ask the questions. Okay, let's start, guys. I have a table for you. You want to build a shopping cart. Tell me what do you want now. You want AP or shopping cart? Shopping cart, shopping cart, shopping cart. So there is a partition between the students. You are selecting this and that. So I am not writing because you are divided. Okay, at least go to next bank transfer. Bank transfer. Bank transfer. Ah, very good. This is right. All of you written correctly. Bank means consistency mandatory. Very good. Chart messages. Chart messages. Ah, very good. All written correctly. AP. Authentication systems. Auth systems. Authentication systems. Authentication systems. Very good. This I am not selecting. Auth systems definitely CP. Not this. Ticket booking. Ticket booking. Ticket booking. Ticket booking. Ticket booking must be consistent system. You cannot go for a overbooking, right? One ticket pending for the flight. One ticket pending for the flight. Both Saurav and Abhishek are trying to book. You should not allow both to book. Right? That's what it should be accurate, correct. It should be consistent. Metadata coordination. Metadata coordination is a kind of zookeeper. Right? It is doing zookeeper. That definitely should be CP. Messaging apps. Very good, AP. Social media apps, social media feeds. Social media feeds, if you give wrong data also, what is the urgency, right? Go for availability important. Social media, whenever you open the Facebook, it should open immediately to you. If Facebook is not working, your mind will not work. Facebook, Instagram should open immediately to you. Whether you are seeing right data, wrong data, secondary for you. It should open high available. Provide inconsistent data, no problem for them. Inventory management is a CP, very good. So one you have divided, guys. Inventory CP, correct. So go to first one, shopping cart. Now think and tell me. Shopping cart, all should come to single. For shopping cart, indirectly search also added, right? Shopping cart, search are the interrelated operations, right? Shopping cart, search. When you go to Amazon e-commerce platform, first you will search for a product, searching products, then adding to the cart, then placing order, then inventory cross checks, then payment gateway. See the e-commerce application. These are multiple modules are in our current terminology, multiple microservices, right? So shopping cart searching should be high available, guys. You are searching for product. If I show the wrong price, what is the problem, guys? I am displaying a wrong price, or I am displaying a product which is not available in the stock. What is the problem? No problem. Right? AP, yes. This should be the AP. Shopping cart, product sets, shopping cart, product sets, these are all high available. And bank transfers, financial transactions, you need accurate data. CP, chart messages, AP, authentication systems must be consistent, ticket booking consistent, metadata coordination, consistent, messaging apps, social media feeds, and inventory management, and video streaming apps, AP. Means if, for example, uh, any title of the video is played wrongly, or a metadata of the video displayed wrongly, what is the problem? You given a some metadata, that some mistakes, later you updated it, the updated data if I show you slowly also no problem, right? Chat messages, how AP? Chat messages, suppose you are chatting Amar, you are sending a message to your friend Ashwant. If Ashwant is not replying also, any urgency is there? If you are transferring amount from your account to Ashwant account, problem is there, then you will cry. You are sending a message to Ashwant, hello Ashwant, how are you? If it is not going to Ashwant also, if system is not available to take the message and deliver it to the Ashwant also, no urgency for us. That's what, that's how you have to decide. Yeah, yes. Again, that is the next point, Sashi. That's the next point, Sashi, we are going to talk. Async, that also makes us, in this context, we have to choose the distributed system communication styles, either synchronous or asynchronous. Again, you have to choose between synchronous and asynchronous. Okay? Okay, this table is clear. I have the answers in the next slide. You see, I think you selected correctly, right? No, inventory should be accurate, Nitesh. Inventory must be accurate. Inventory, ticket booking, both are same. I given in a two styles, but inventory is, it is nothing but how many laptops available in the store, or how many tickets available in the bus, how many seats available in the flight, how many mobiles are in stock. That should be accurate. See, before, Nitesh, when you are searching for a laptop, I will say this laptop is available with this configuration. No problem. When you are placing order, then I will cross check my inventory. Then suppose inventory item not there, this laptop, then I'll say, sorry boss, I can't add this to the place order. You can reject that time. Right? Okay. So we are able to understand what is required for us, whether you want A or C for a distributed system. Another important trade-off, latency versus consistency. Latency versus important trade-off this is. So in distributed systems, especially with the replicated data, that's what we have taken use case. You got a choice. You choose either consistency or latency. Replicated data means consistency or latency you have to choose. Now, what is consistency? As already we have seen, again I written a different point. Consistency means all users see the same up-to-date data, correct? All users see the save up-to-date data. You have a node A. Consider this is a master. Somebody is writing the data here, writing x equals to 10. Okay. Now there is B, C, and D. This has to be previously here x equals to 5, x equals to something 5 is there, x equals to 5 is there. So previous x5 is now new write happened to 10. Okay. Now it has to be replicated all three. So if anybody hitting the B or anybody sending a read request for C, anybody sending a read request for D, all has to respond with the updated x value, which is 10. If that is happening, you say this is a consistency. All users see the same and updated data. Then a consistency. No matter which node they hit, they go for a B or a C or a D, or you may have a 20 nodes, whatever, they have to see same and updated data consistency. Latency, user get a fast responses by reading nearby data. So even those may be slightly outdated data also. Latency. Now, so you have to choose, you want a consistency or latency? Do you understand how you will choose consistency or latency? Okay, let's go to the next slide. Why this trade-off is important for us? When a write operation happens, it takes time to propagate the changes to all the replicas across the network. When a write operation happens, it takes time to propagate all the changes to all the connected replicas. And until that, it has to wait for the acknowledgement. I think in the replication mechanism, I told you the full diagram. Suppose if write operation is happening to the master, then master is not responding immediately to the user. Master is not responding immediately to that, boss, your write is done. Master is talking to read replica 1, confirming to 2, 3, 4, then all are confirmed. Finally, it is telling that, okay, boss, write operation completed successfully. So it takes time. Is this clear? Whenever you do a write operation, then it takes time to propagate changes to all the replicas, and it has to wait for acknowledgement from all the replicas. It's a time-taking process. You have two options. Do you want to wait or you don't want to wait? Do you want to wait? Yes, I want to wait. If you wait, you will get a consistency, boss, but higher latency. You don't want to wait. Latency low, but inconsistent data. So you tell me, you want to choose a latency or consistency is just based on your use case. You want to wait until the acknowledgement is coming for write operation? You don't want. Actually, the same point, whatever I am telling now, I discussed already in a different angle. That angle also will come forward now. See, do you want to wait? Yes, if you wait, you will get accurate data in all the replicas, high consistency, but delayed, right? You're getting a delayed response. But if you don't want to wait, urgently, you want to send a response, then your latency is less only, very fast you're responding to the user, but you will lose the consistency because you will lose the stale data. So you want a strong consistency in applications like banking, booking apps, etc., inventory. We discussed multiple examples, right? In this, if strong consistency if you want, then latency is high consistency is agreeable by all. You can say consistency is high. High consistent, high latency. Systems are consistent systems, but latency is high. If you want eventual, you link here. If you wait, what you are getting? If you wait means, is it a strong or eventual? Or read it again. Eventual consistency means AP systems gives you the eventual consistency. Immediately responding with high available, low latency, high available, low latency, high available, but consistency coming after some time. Meanwhile, you're serving the stale data. May differ temporarily, chat, social media, etc., etc. So now tell me here, if you wait, what consistency you are getting? Strong consistency. Very good. If you don't wait, then also you are getting consistency, but eventual consistency means temporarily user is telling that I don't want to wait. Give me results fastly. Then you are giving whatever available wrong data with you, are giving that wrong data to user. If that user comes again, you may give again wrong data. That user comes again, you may give a right data, because by this time eventually the data is replicated here. Got it, guys? And second angle in this, so CP systems provides you the strong consistency, but the latency is very high. And AP systems provides high available and eventual consistency, they provides the low latency. And another replication, when you do replication, this also makes a factor. When you do replication, there are two ways to implement replication. This also I have shown you with the diagram clearly. Replication can happen synchronously or asynchronously. What if the replication is happening synchronously? Synchronously means you are waiting, right? Synchronously means you are waiting. You are waiting means you have a consistency and low consistency is there, high latency. Or instead of this, I'll use a term here. What I'll use here, guys? Can I say high latency? HIGH, high latency. And also, can I say the strong consistency? About terminology, I'll use this. Waiting means you are getting a strong consistency and high latency. And asynchronously, I don't want to wait. If you don't want to wait, in that case, you have to go with the asynchronous only. Asynchronous means do write operation, respond to user later, slowly, asynchronously, it will do the replication over the read replicas. So immediately I want means you have, let me to take this points only. So tell me, replies immediately, asynchronous. What about consistency? Eventual consistency. Immediately responding. Immediately responding means the latency is the low. Latency is the so clear, guys? That's about in and outs of a CAP theorem. Next, we have another theorem which is an extension of CAP theorem called Pace LC theorem. We'll see that in the next session.